Let's understand the architecture of the our model. Uh, at first, we have applied a convolution layer in which a 2D convolution is applied with kernel size of 3, stride 2, and padding 1. There is then there is batch normalization, and then there is activation function, which we use as a hard switch activation function. There is bottleneck block, which greatly helps to reduce the size of the model while keeping it efficient. Then there is again convolution layer. Then there is a pooling layer in which adaptive average pooling is used. Then there is a fully connected layer. Let's see what is inside the bottleneck block. In the bottleneck block, there is a one cross one, that is also known as a point-wise convolution, is applied, which is highly computationally highly efficient than the normal convolution. Then the two layers are uh, of the depth-wise convolution are applied to reduce the dimensionality, and then there is a squeeze excitation layer is applied, uh, and then again there is a 2D convolution is applied, and then there is a batch normalization. Let's see what is inside the squeeze excitation. In squeeze excitation, first there is average pooling layer, then there is convolution, then there is ReLU, then there is convolution, then again there is a ReLU activation function is used. The main purpose of the squeeze excitation is that this block acts as a channel-wise attention mechanism, enabling the network to recalibrate its feature maps while learning the importance of the different uh, channels. It focuses on the more rich features while keeping the model efficient. The hard switch activation function is based on the ReLU itself. It is there is also another activation function which is swish, but hard. They are almost similar, but the hard swish function is computationally more efficient than the swish activation function. That's why we have used the hard switch function. Uh, then let's understand how the model training is happening here. Uh, For the loss function, we have used the cross entropy loss criteria. Then for the optimizer function, we have used the Adam optimizer with the learning rate of 0.001. It is the rate with which the model will learn the new updated weights to minimize the loss function. Then to evaluate our model, we have used it, there are a number of performance parameters of the model. We will calculate and store these model parameters during the training, so that we after the training we can comment on the performance of the uh, this model. Then there is a here we have defined the training training model, which will require the uh, architecture of the model, the criteria for the loss function. Then there is how we are optimizing. Like there are a number of ways in which we can optimize our model. Optimizing our model means updating the weights to decrease the loss function. Then we will be training this model on the 25 epochs, and the training process, as we already know, is the same. There will be forward pass, and then there will be calculation of the loss function. Then to decrease that loss function, uh, there will be a back propagation, and the uh, um, weights will be updated for all the all given inputs, and then it will the process will repeat for the given number of epochs. At the end, the model will be saved in a file. And here you can see we have calculating the performance parameters during the training itself. Let's now test our trained model, how it is performing on the uh, test image data. So for the given image from the test data, it is predicting that it is the leaf of an apple tree and it is infected with the apple scab.